Sir, you're live now. You can start.
Yeah, you can hear me?
Yes, sir, you're audible.
Okay, so good afternoon to the learners of Aqueous Corrosion and Control NPTEL course. I do hope that you have been having good exposure to various forms of corrosion. In the last meeting, we had a very useful discussions, and it was, in fact, I was very happy to hear that you have been following the lectures very closely, and you have come out with excellent questions. So today, it is in the second question and answer session. So I'll be happy to talk to you and try to clarify any kind of doubts that you have. Please shoot your questions, and along with me, Ms. Kirtika Ganeshan, who is the TA, is participating in today's interactive sessions. Please, send your questions, and we'll answer one after another. Thank you very much.
So the first question we have, whether Tefel slope vary with nature of metal and its microstructure? Does it have any, like based on the formula, it does not have any metal related parameter?
Yeah, see, in principle, first of all, when you talk about tapered slopes, there are two types of tapered slopes, right? In a corrosion process, one is a cathodic tapered slope, where the cathodic reaction, is occurring. For example, if you take a steel and immerse it in sulfuric acid, the cathodic reaction predominantly is hydrogen evolution reaction. So it's a cathodic tapered slope. On the other hand, if you are going to immerse steel in, say, neutral sodium chloride solution, you are going to have predominantly a cathodic reaction, which is oxygen reduction reaction. Now, the tapered slopes for both of them are different, and apart from that, the tapered slope for even for a hydrogen evolution reaction can be different depending upon which is the dominating mechanism for hydrogen evolution reaction. Generally, for hydrogen evolution reaction, you would expect about 110 millivolts per decade, right? Now, that is the case where the alpha is equal to 0.5, right? The transfer coefficient is 0.5. Now, if the transfer coefficient alpha is changing, you'll find that the beta value, the cathodic tapered slope, will change. Now, the alpha that we talk about could change depending upon the metal surface, okay? So there is a possibility that the alpha will change. So there is a small change in the alpha value. But however, I would say that for hydrogen evolution reactions, you will get the order of 110. This is the kind of tapered slope you get it. Provided again, it is not diffusion controlled, right? If it's a diffusion control, then the slope, becomes almost like infinity, because the cathodic current does not change with respect to the applied potentials. So that's about it. Now let's take to the anodic tapered slope. The anodic tapered slope is nothing but a metal dissolution reaction. Now in this case, both the N value and as well as the alpha value will change, right? In the N value of a metal oxidation, if it is, for example, zinc, N equal to 2, this oxidation state. And so the beta value will be off the 120, right? So about 60 may be there. If there are 3 electrons are involved, for example, the value of beta is going to change. So it's possible that this changes. Microstructural variation, in my view, may not cause a very significant variation in terms of tapered slopes. What could change is the exchange current density for the reaction could change, okay? And so the you noticed earlier, right? For example, platinum, the exchange current density for hydrogen evolution reaction is so high. It's in terms of milliamperes per centimeter square. If you take, for example, zinc, it could be 10 power minus 9 ampere per centimeter square. But mercury, it is even more or less actually, right? The exchange current density depends significantly on the metal, okay? But the tapered slopes are not going to vary too much, especially with the cathodic reaction. And the anodic reaction, of course, each metal may have its own oxidation states. And so when the oxidation states changes, then the tapered slope changes. Okay. And of course, sometimes you may form a nice passive film, you will not even see a tapered region at all. Okay. So that's also possible. If the passive region starts immediately, you don't see a linear region in the potential versus log current scales now. Okay. So tapered regions may be missing over there. So these are possible, but this is broadly, I would say, you should analyze, tapered slope, taking them into considerations. Okay, but you are going to look at very simple systems. For example, hydrogen evolution reaction. We talk about Balmer mechanisms. We talk about Hierarchy mechanisms. Then the tapered slope value changes, but that is a pure electrochemistry that you normally deal with now, actually, right? Yeah. So I hope it's clear. If it is not, you please send me again questions, and I will explain to you further.
Thank you, sir. The next question is how Evans diagram is constructed for ICCP. Unlike for sacrificial protection, anode is inert in this case, and therefore its plot will start from above of metal to be protected in Evans diagram.
See, the Evans diagram is meant only for the metal that is corroding, right? If you take the Evans diagram, right, the Evans diagram, you will have a cathodic reaction coming like that, right? Cathodic reaction like hydrogen reduction reaction coming like that. And you have an anodic reaction where, let's say, steel is getting corroded and the kinetics is like iron going as iron 2 plus 2 electrons. So you have anodic tapered slope and you have a cathodic tapered slopes coming like that, or cathodic kinetics coming like that. And the intersection points becomes your I car, and then you have the E car here, right? Now, in the Evans diagram, the anode does not come into picture at all, okay? So, especially for ICCP, right? You must understand one thing, irrespective of what the anode use, okay? The current, the corrosion behavior of the metal depends upon the potential applied on that particular metal, right? Whether you apply it through sacrificial anodes, whether you apply it through the ICCP method, it does not matter. In both the cases, the corroding metal experiences a potential shift towards the cathodic direction, right? So the metal has an anodic kinetic line, right? How much you are moving the potentials towards negative direction, that only decides the corrosion rate. It does not matter what extent anodic polarization occurs, okay? Now, probably I'm getting a feeling that you are looking at, in some cases I've shown the tapered slopes for the sacrificial anodes in one of the lectures in cathode protection that I've shown, right? Yeah, but see, that is somewhat different from that of the your impressed current anode systems. In ICCP anode systems, you are simply forcing the current into the soil, right? In the ICCP, the purpose of the anode is to push the current into the soil. The rectifier pumps the current into the anode. So it does not matter what kind of kinetics reactions are occurring on the anode at all, because you're brutally forcing current on the anode, and the anode in turn pushes the current into the soil. So it does not matter what is the slope of for the impressed current anode systems. Now, of course, if the ICCP anode polarizes much, then you require more voltage. For example, it may be easy for platinum to push more current. It may be difficult for iron silicon anode to push current. That means you need to apply more voltage on iron silicon anode as compared to that of the platinum. Even small amount of voltage will push more current into the soil. Okay. So what we're trying to do in the ICCP is whatever there is current required in terms of amperes, we're simply pushing it through a rectifier. We don't really care about what this anode kinetics are. The only problem that happens is the platinum can carry more current. I can push more current, but in terms of current density, I would say, right? Whereas in the case of iron silicon anode, you can't push too much of current density because then the anode will start destroying. So that is the limitation. So we don't really care about the polarization kinetics of the impressed current systems because of the rectifier. But yes, the polarization kinetics of sacrificial anodes are important because you should not polarize. If the sacrificial anodes polarize, then it can have more driving voltage, right? More the polarization, less the driving voltage, right? So that's what I think is to be taken into account when you compare the ICCP anode versus the sacrificial anodes. Okay, and thank you for the question.
Thank you, sir, for answering. The next question is on knife line attack.
Yes.
Knife line attack takes place from bottom layer of alongside weldment to top while we proceeded with the passes of welding. It is due to the reason that during each pass, temperature is in sensitization region from pass already completed earlier. But why is the failure or sensitization only confined to region alongside weld? Why not take place in HAZ, heat affected zone, which may also be subjected to sensitization temperature, like in traditional single pass welding process?
Yeah, it's a good question. If you have listened to my lecture, you would notice a few things. The knife line attack occurs only in stabilized grade stainless steels like 321 and 347. That's a very important point. It does not occur in low carbon stainless steels. Okay. Now, how does a low carbon stainless steel offers resistance against IGC? It offers resistance against IGC because you have lower carbon content in the low carbon stainless steels, and so the chromium carbide formation kinetics is lowered, right? If you look at the TTT diagram, the nose of the curve moves towards right side actually, right? So lower the carbon content, you find that it is very difficult for the chromium carbide to form. And when you start welding, and welding occurs at higher temperatures, the heat affected zone, the temperature lies in the range, let's say about 400 to about 850 or 900 degrees Celsius. That's the temperature range where the heat affected zone is now facing. Now, that is the region where the chromium carbide formation occurs, provided enough time is given. Please see that the sensitization depends upon the temperature at which the sample or the structure is kept and the time for which the temperature is held actually, right? Because chromium carbide formation is a kinetic process, takes time. So that means you are going to have a lower carbon content. It takes long time for the chromium carbide to form. So low carbon stainless steel inherently has, lower tendency for sensitization because when you start welding, you raise the temperature and then starts cooling down. And that, the time taken for cooling down is lower than the time taken to form the chromium carbide in the low carbon stainless steels in the heat affected zone. Now let's look at how the sensitization is avoided in the stabilized grade stainless steel. The stabilized grade stainless steels, what we do, you first of all take it to very high temperature, like 1100 degrees Celsius. You dissolve all the carbides actually, and then quench it. Then take this to a temperature around about about 900 to 1000 degrees Celsius. What happens in that case? In that case, the alloy forms titanium carbide if it is allied to 3 to 1. If it is 347, it forms niobium and tantalum carbide. So the niobium and tantalum carbides are present in the stabilized grade stainless steels. All the carbons present in the stainless steel, they combine to form these carbides. When the carbides are formed, automatically the carbon content of the stainless steel decreases, or the free carbon content decreases. So when you're going to do welding, when you're going to heat it, it doesn't form chromium carbide because the carbon is now taken away by titanium in the case of 3 to 1 and tantalum and niobium in the case of 347. So when you weld it, now nothing happens. Even though the interpreted zone faces the temperature between 450 to, let's say, about 9 degrees Celsius. Now, from the interpreted zone, you move very close to the fusion zone, right? When you move very close to the fusion zone, the peak temperature increases, right? The peak temperature increases. Now the temperature is not between, let's say, 450 to about 900. As you go very close to the fusion zone, the temperature can go up to 1100 and 1200 degrees Celsius within the base metal. So what happens when you go to 1100 to 1200 degrees Celsius, the tantalum carbide, niobium carbide, titanium carbide, they're all dissolved. So when you cool it down, actually, now what happens? Now the titanium carbide, tantalum carbides are no more existing. Now the carbon is gone into the alloy steel. Now the carbon is free. It does not have chromium carbide. It does not have tantalum carbide. Does not have any of these carbides. So please see a zone very close to fusion zone. Very close to fusion zone, you are not having any of these carbides. There's no titanium carbide, no tantalum carbide, none of these carbides. But in the typically interpreted zone, you still have the carbides. Okay, that means carbides are still remaining. There is no free carbon in the interpreted zone. Whereas close to the fusion zone, there is a free carbon available now, right? When there's a free carbon available, now it has a tendency to sensitize if you raise the temperature in the range of 400 to 900 degrees Celsius. So the zone close to the fusion zone, because the carbon is free, and if you raise the temperature in the range of 400 to, let's say, about 800, 850, 900 degrees Celsius, now there's a tendency for the carbon to form chromium carbide. The tantalum carbide now form only at high temperatures. Titanium carbide forms at high temperatures. The lower temperatures, the chromium carbide forms. Now, let's take a thick weld now. Suppose I am going to weld a thick plate of, let's say, about 1 inch thick plate and above. What I do? I do multi-pass welding. So I start welding at the root first, then another layer, another layer, another layer like this. So when I start welding the root undergoes what you call the welding. Now there is no sensitization taking place. But what happens now? In the root, in the base metal, close to the fusion zone, titanium carbide, niobium carbide, tantalum carbide, they're all dissolved now, right? Now you look at a situation where you are building up one after another. So you are having one layer, you keep building up now. When you start building up, the bottom layer is a typically interpreted zone when you go to the top here, right? Because it is about, the interpreted zone is about 2 to 3 millimeter distance from the fusion zone. So you find that the so-called the narrow zone now becomes the interpreted zone to the top of it now. And so what happens? Now there's a free carbon, and that free carbon combines and forms chromium carbide. The chromium carbide is formed, and so there's a sensitization taking place. So essentially, you put it the other way around, the sensitization occurs in the stabilized gate stainless steels. The lifeline attack is nothing but sensitization. The only difference is that in this case, two things happen. The existing carbides, tantalum carbide, niobium carbide, and a titanium carbide, they dissolve in the first welding time and become pure carbon. And as you start building layers, and the bottom one has now a temperature which is equal to like somewhere between 400 degrees Celsius to 800 degrees Celsius, and you have enough time to cool, right? So it forms sensitization. So sensitization, that's why it happens at the root of the weld, doesn't happen at the crown of the weld actually, right? The crown of the weld is last one. So knife line attack occurs very close to the fusion zone and the root of the weld, not on the crown of the weld actually. I hope you follow this point, okay? And you still have some doubt, do let me know. I will again try to see how best I can explain to you.
Thank you, sir. There is one follow-up question to the previous question on ICCP. What reaction are occurring at anode for ICCP, which is causing the ionic current movement towards the cathode?
Yeah, it's very, very interesting and very important question now. See, let's take any electrochemical cell, right? Let's take any electrochemical cell in simple terms, right? One is an anode, other is a cathode, right? And you are passing a DC current. Please understand, you are not talking about AC current. You are passing a DC current, and the terminal which is positive, you have an anodic, anode. The one on the cathode is a cathodic current. And cathode, there is a reduction reaction, and the anode, there is an oxidation reaction, right? So now we are talking about ICCP. Now assume what happens ICCP in anode. What happens? The anode, the electrons leave, right? The cathode electrons go inside. The anode, what happens? The electrons come out of it now, right? How does the electrons come out of it now, right? The electrons can come out of it if, for example, water can get oxidized, right? For example, if water is leading to oxygen evolution reaction, right? You put H2O is going as O2 plus 2H plus, right? So there are electrons now, okay? So these electrons now come out of it now. So always the ionic current converts to electronic current, or the electronic current converts to ionic current. There is always any electrochemical reaction. Without electrochemical reaction, there will be no change of current. Electronic current into ionic current will happen only when there is a thing like this. Same thing like a battery also. Like in battery, what do you do? When you are going to use a dry cell battery, okay, you find at the anode, zinc is getting dissolved. Electrons are coming out of it now, right? Okay. On the other side, you have manganese dioxide is getting reduced. So you find that the ionic to electronic conductivity comes only through electrochemical reaction occurring at the electrode surface. If it is the anode, there has to be an oxidation reaction very clearly. Okay, in this case, the water may get oxidized. Suppose in some cases you have chloride ions, Cl minus ion. What happens now? With the chloride ions, what happens now? The chloride ions become chlorine gas plus 2 electrons. If it is the water, what happens? The water has got H plus and OH minus, right? So you have OH minus will convert into oxygen plus electrons come from there. Okay, so these are the ways that the ionic current is transformed into electronic current. The electronic current is transformed into ionic current. Okay, that's what is expected to happen. Thank you for the very good question.
Thank you for answering, sir. The next question is, kindly explain cathodic loop for active passive metal.
Can you please repeat the question, Kirtika?
Kindly explain a cathodic loop for active passive metal.
Yeah, see, I mean, if it is active passive metal, the anodic current, kinetics changes, right? In active, passive, transpassive metal, if you have an Evans diagram, like you have potential here, and current in this axis. Now, what happens? The current increases with potentials, and then again it reduces and becomes passive region. It goes like this, right? Okay, so in that case, when you say cathodic protection, we are talking about, see, cathodic protection always talks about a potential below the corrosion potential. Please understand that. You cannot, you have to bring the potential of the metal below the corrosion potential, right? So below the corrosion potential means there is no passivation, at least in that sense of it now, right? So whether the metal is passivating or non-passivating, cathodic protection involves bringing the potential of the metal below the corrosion potential, right? In the anodic protection, what do you do? The potential is shifted towards the anodic direction and kept it on where? Kept it at the passive region, right? At the passive region, because then the metal has got a current which is equal to passive current density, and that is the passive current density is the rate at which the metal is dissolving now. So it doesn't matter whether the metal is having active passive transition, or the metal is not passivating at all. It doesn't matter. You are simply concerned with reducing the potential of the metal from ECAR value to a lower value. Actually, that's what we do. That it doesn't matter at all whether metal is passivating or non-passivating. Okay.
Thank you, sir. We have the next question is, kindly guide whether conversion coating can be used as a standalone coating for corrosion control. For instance, example is manganese sulfate.
Yeah, you were right. I mean, this question, of course, somebody asked, see, manganese sulfate coating, manganese, is manganese. See, only manganese coatings are exceptions. Okay. The manganese coatings are exceptions, actually. All other conversion coatings are not, or standard coatings. And of course, manganese coatings are very rarely used. Yes, you are right. If you are talking about manganese, type of coatings, it can be standalone coating, because see, actually, many times the manganese coatings are also consist of certain kind of resins, right? Some kind of binder. People add along with that some kind of alkyd or something like that. Okay, so you normally manganese sulfate coatings are not normally done independently. They are normally done along with some kind of resin or binders. Yeah, your question is right. Okay, only in the case of manganese things, it can be standard coatings, but that is used very, very rarely. People don't generally go for it on the coating. Okay. Yeah.
Next is kind of a general question. Kindly share some insight on software modeling tools available for corrosion study.
Yeah, I don't want to advertise actually. Okay, one of the software is COMSOL. COMSOL has some software which it talks about it now. See, again, corrosion studies is a very broad thing now. Okay, if you are talking about curve fitting, if you do let's say electrochemical corrosion test, for example, you want to determine the ICAR and ECAR. There are softwares available which is instrument, right? There are several equipments like your, Gamry or maybe Parstart or, Slumberger. There's so many kind of electrochemical systems are available. See, please see, I'm not promoting any of this systems, but they are available. But so they themselves have a built-in software, okay, which fit these curves to determine the tablet slopes, and of course the ICAR to get the ICAR value and the ECAR values. Okay, so that is about analysis of data. But you are going to talk about curve fitting, which is, even prediction, something like that. There are, like, for example, somebody is interested in a galvanic, corrosion. Just 1 second. Yeah, if somebody interested in galvanic corrosion, then what happens? They use COMSOL. COMSOL can be used to predict the corrosion, galvanic corrosion rate, actually. Okay, and there are some software available which talks about corrosion happening in crude oil pipelines. Okay, so these are all software which are developed for specific purposes, actually. Okay. Otherwise, yeah, I mean, for all the electrochemical systems, each of the manufacturer of potential stats, they provide their own softwares. Thank you for the question.
Another is a small request kind where the student is asking whether there is a possibility for online demo session of polarization and other corrosion measurements used in the lab, somewhere referred during lectures.
We have to try. See, only thing is, it is a very important one. I mean, I totally agree. Okay, the thing is that we need to have a proper professional recording of that. Then only you can able to get something. Otherwise, if you don't use a proper recording systems, you can't even make out. Maybe I think probably one particular one course on electrochemical experimentation, corrosion experimentation is very important, and I hope that sooner we have one course on corrosion testing and evaluation.
Yes, sir. If I may add, if you're so curious, you can always check out Potential Stats Maker's website to have some knowledge, although not complete demo will be there.
Yeah, it's possible actually.
So the next question is, kindly share some insight on corrosion of rebars.
Rebars.
Yes. Especially they have asked about effect of improper heat treatment or bending causing the stress concentration or different types of corrosion in rebars, and will painting work in corrosion protection and cathodic protection of the rebars.
Yeah, it's another big subject by itself, I think. Ideally speaking, steel is not supposed to corrode in a cement, right? If you've seen the Poolbay diagram, right, for the steel or iron, you'll notice that about the pH about 11, 12, 13, and in the range, the steel does not corrode that much, or the rate of corrosion is so small, we simply ignore that actually, right? So when you talk about cement, the cement, it creates in a pH in the range of 11, 12, which is ideal for retaining the corrosion resistance of the steel. Steel does not corrode that much. So in ideal concrete, when you do, these steel bars are expected to last longer because the pH is in the favorable condition actually. But however, the corrosion of this rebar happens because of the fact that there can be chloride ingression takes place. Then sulfur dioxide ingression takes place. Carbon dioxide ingress can take place. So when these things, the ingress occurs, then the pH is not maintained. It breaks down the pH. The pH can go to acidic region. And if you have chlorides, the chlorides can damage the passive film also actually, right? So these are the problem that happens. Now, what makes the metal to have chloride and all, it depends on the environment. Now, some environment, you have more chlorides. If it's a coastal area, there will be more chloride. And sometimes what happens when you have a concrete, the concrete is sometimes brittle, right? There may be cracks, and through the cracks, these chlorides can go much easier, and then so can cause attack at all here. So the pH of the environment surrounding the steel bar slowly becomes acidic. More chloride, passive film is destroyed. The corrosion occurs at a very high rate. Now, in order to mitigate the corrosion, one way to do is that don't have chlorides. Even in the sand that you're going to use, you must have a very minimal amount of chlorides. If you're going to have more chloride, there's a problem first of all. The second thing that happens is that when you're going to have concrete, the concrete can be brittle. If there are cracks that happens actually, right? What happens now when in the concrete, when the cracks happen, through the cracks, this in the environment will seep through and start corroding at higher rate now. So you need to avoid cracking of the concrete as much as possible. Actually, okay, and so and of course people can add inhibitors. Somebody does fusion bonded epoxy. Somebody does degalvanizing, for example. There are various ways people do that, but all of them are intended to reduce the corrosion rate, and so the steel rebar will have a longer life. See, actually, one thing I forgot to tell you earlier. When iron corrodes and it forms iron chloride, the iron chloride will be subsequently converted into iron oxide, magnetic oxide. The volume of these oxides are much more than the volume of the metal now. Okay, so when that happens, then it pushes the concrete, and the concrete, just flags out actually, right? So that's one of the problem now actually. So the problem of corrosion has two problems. One, it affects the metal. Secondly, it also affects the concrete casing on the surface. They break and start, and having easy access to the environment actually. Okay, so causes the corrosion problem. So that means you can have a coating such as some people apply zinc coating. Somebody does what is called as epoxy coatings, and you also talked about cathode protection. The cathode protection is very tough here because when you have all these concrete rebars, they should be electrically shorted now. Okay, otherwise what happens? Current will flow only in certain steel rebar piece, but majority of them may not have receive the current and all. So cathode protection is a bit more difficult, but people go for epoxy painting and all this, even zinc coating, and people do that. Okay, that will minimize the corrosion of the rebars.
So the next question, sir, is based on the mixed potential theory for a galvanic coupled zinc ion. Can we tell whether the net current for zinc hydrogen equilibria at the new equal for zinc and for iron, whether the net current for the zinc hydrogen equilibria at the new equal line and for iron hydrogen equilibria at the new equal line is same? Or can we tell that it is shifted to the couple formation? Net anodic current supplied by zinc equilibria is equal to the net cathodic current received by the iron equilibria at the new equal.
Yeah. Would you mind, reading that again one more time, Kirtika?
Yes, it is based on the events diagram for a galvanic couple, for example, zinc iron. So, whether the net current for zinc hydrogen equilibria at the new E-core line, that is I couple of anodic minus I couple of cathodic for zinc, and for iron hydrogen equilibria at the new E-core line, for iron is the same. Or can we say that it has shifted to a potential on the couple formation where the net current, anodic current supplied by the zinc equilibria is the net current received by the iron equilibria at the new equal?
Yeah, there's several questions here. See, let me try to understand this. See, when you're doing a galvanic coupling, right? Suppose zinc is now shorted with iron, and assuming that the electrolyte does not offer much resistance, suppose sometimes you coat it on the surface only, right? Then what happens? The potential of the bare metal, the potential of the coating are the same potential because they are electrically shorted now, right? So in that case, when you have a galvanic coupling, in the galvanic coupling, you will see that the steel and zinc has the same potential now. Now, when zinc and steel have the same potential, what does it mean? It means, see, when you immerse simply steel and immerse simply the zinc now, zinc has got a lower E-core value, minus about minus 1 point something, right? 1.1 or something like that. So zinc has got lower corrosion potential, right? Whereas the corrosion potential of iron or steel is very high, right? So when you do a galvanic coupling, what happens? The potential now you're shorting them together, right? The potential of the steel will come down. The potential of zinc will go up because zinc has got a much more negative potential as compared to the potential offered by the steel here. So when you shorten it now, the one with more negative potential will start moving up. The one with relatively more positive potential will move down. So when the potential of iron is moving down, it is your polarizing cathodically, right? That means the iron corrosion rate is decreasing. Now, when you talk about zinc, for example, its potential is moving up. So it is polarizing anodically. That means zinc is going to corrode and steel is getting protected, or steel is getting protected at the expense of the zinc coating or zinc slab at all. That's what happens in the galvanic coupling, right? So that's how it happens, and you can able to make some. See, this all can be computed using a COMSOL, provided, of course, you must know the table slope. The table slopes are different, and even the area of the sample, all are required now. Okay, if you do this, it's possible for you to compute the potential, and current distribution. Also, sometimes you'll have anode and cathode separated. You want to know the current distribution along the anode and cathode. All these are possible now because these governing equations should be known. Once you know the governing equations, now it is a matter of writing algorithm to get the answer for that. Okay. Thank you very much for the question.
Yes, sir. With this, we move to the last question of this session.
Okay.
Is SEC incorporated in design calculation for mounded buried vessels? These vessels are laid on, molded buried vessels. These vessels are laid on sand foundation and subjected to settlement with time. Settlement studies are conducted periodically and corrective action to relieve stresses are taken when the reading exceeds the permissible limits. Does these readings consider SEC at nozzle joints in buried vessels, which is used to withdraw or fill product? Pipeline connected to buried vessels are on rigid support, while buried vessels are laid on the sand beds. Thus, there will be a relative settlement vessel, which will basically it's about the SEC at the nozzle joint.
Yeah. Would you mind again slowly going through the question again? I am still not getting a clarity
Yes,
in
sir.
what the question is.
Is SEC incorporated in design calculations for buried vessels?
Okay, so is SCC, that is, I guess you are talking about stress corrosion cracking, right?
Yes.
Okay, so SCC means, yeah, see, I mean, stress corrosion cracking occurs, it's a conjoint action of stress and the environment on a metal, right? Okay. So if you have stress and then there is an environment which is going to promote SCC will happen. Okay. Now, if there is a SCC occurs, then you do a cathode protection. Then it'll suppress. In fact, one of the ways to mitigate corrosion is by cathode protection, right? Isn't it? So cathode protection will reduce the corrosion rate of it. Now, what is the potential that is required? I think there are various standards. The NACE standard, for example, talks about passing the current on the structure to be protected, such that the potential of the pipeline, which is cathodically protected, okay, the potential of the pipeline which is cathodically protected, okay, should be equal to minus is equal to minus 0.885 volts with respect to saturated carbonyl electrode, right? This is what it is. Now that is for normal, coating defects, all this happens in the home. But then if there are major problems, then of course you have to pass more current, right? So that means the criteria is to see that the potential of the pipeline or structures with respect to the reference electrode, which normally we use what is called as copper sulfate electrode. Okay, that electrode, it should be minus 0.85, right? That's what it is. So how much current will pass and all depending on the system. Some system may need more current, some system can need less current. So, but then end of the day, if you're going to hold it at minus 0.85, the corrosion rate is very negligible and you are safe in taking this material to your place or anywhere else. Yeah. Okay. Are there any questions?
That's the final question.
Okay.
There is a one follow-up though for the galvanic couple.
Okay.
So the question are so the doubt is like we say that when we supply current, polarization occurs with I anode minus I cathode, which is equal to the supplied current. Whether can we say that at mixed potential, zinc hydrogen equilibrium is supplying current to iron hydrogen equilibrium or vice versa?
Can you repeat the question if you don't mind, Kirtika?
Yes, sure. So we say that when we supply a current, polarization occurs. It is the current of I anode minus I cathode. Can we say that in a mixed potential system that zinc hydrogen equilibrium is supplying current to the iron hydrogen equilibrium or vice versa? Like whether this metal hydrogen is giving that
Yeah,
current.
see, in mixed potential theory, if you see the cathodic tapered slope of the hydrogen reduction reaction and the anodic tapered slope of the zinc dissolution process, they intersect the point, right? The point of intersection is equal to the corrosion potential and it's equal to corrosion current density. Okay, so anything you move away from it, automatically there's something happens. When you move away, suppose if your E-car is, let's say, minus 500 millivolt with respect to, let's say, saturated carbon electrode, for example, and you are going to take it to minus 300, you will have anodic reaction taking place. So you're going to, let's say, minus 1.2 volt, the cathodic reaction will take place, right? So essentially, it depends upon, this is about corrosion, right? Suppose it's not a corrosion, if it's equilibrium system. What is meant by equilibrium system? For example, I have copper sulfate electrode. Okay, I have taken a copper sulfate solution. I put a copper electrode here and I measure the potential. Then you get is equal to equilibrium potential now. Even there also, if you're going to make it relatively negative, that will undergo a reduction process. You make it a little more positive, that will be oxidation process actually. That's what essentially means over voltage, right? And the over voltage is positive, then you get corrosion. And the over voltage is negative, then there's going to be cathodic reaction taking place, right? These are the ways that it happens. Good afternoon. Yeah. Thank you so much.
Yes, sir. With this, we have answered all the questions for the session.
Thank you so much, and it's a very, very, very nice questions, and all the learners have, it appears to me that they're really enjoying the course. I do hope that this course is useful for a better understanding of the corrosion engineering, I would say, and as well as science. Yeah. So thank you very much. If there are no questions, let us thank all the participants, and I would like to thank personally Kirtika for coordinating it and doing a wonderful job actually. Yeah, thank you so much.
Okay,
Thank you,
so
sir,
we're
for
closing the
answering.
session.
So thank you so much. Yeah, thank you. Bye.
Okay, bye.